Today we want to look at how we can solve trigonometric equations algebraically. And when we do that, just like we have done anytime you're solving an equation, you isolate the term you're solving for. In this case, we're going to isolate the trig function. So for this simple trig equation, I'm going to divide both sides by 2. And we get that the sine of x equals 1/2. Now, if we think about solutions to this according to the graph, and I were to graph the sine of x, and I'm just going to graph 2 periods right now. The sine of x would look something like this. But notice it's going to keep on going on and on. So if we graph y equals 1/2, there are an infinite number of solutions. So we're not going to use arcsine in this particular case. If we were just to look, think about where is the sine of x equal to 1/2 within 0 to 2 pi. We know that the angle would have to be, if the sine is 1/2, the angle would have to be either pi over 6 or 5 pi over 6. But we initially didn't put any restrictions on the interval that we're looking at, and if you go back and look at the graph, there are an infinite number of solutions. So to account for all of those solutions, we would say that x is equal to pi over 6 plus 2 pi n, because 2 pi is the period for the sine and n is an integer, or x equals 5 pi over 6 plus 2 pi n. 2 pi is the period and n is just an integer. This would cover all of the solutions to that particular trigonometric equation. Okay, again, I want to solve this equation, and we want all the solutions. So we're going to isolate the term that has a trigonometric function by adding the sine of x to both sides. And I can subtract the square root of 2. So twice the sine of x equals a negative square root of 2. Divide by 2. And we get a negative square root of 2 over 2. Now we have to think about where is the sign negative. And the sign is negative in quadrants 3 and quadrants 4. We don't want to use the arc sign right here. Unless we're told to use the arc sign, we're looking for all solutions, we're not going to use the arc sign. So in quadrant 3, the reference angle would be pi over 4. But in quadrant 3, x is going to be equal to 5 pi over 4. And we have to add our 2 pi in. Or x equals, fourth quadrant is 7 pi over 4 plus 2 pi in. This would cover all of the solutions that would make our initial equation a true statement. Okay, here's another equation that we want to solve. Again, we're going to isolate the trig function. So we want to know where the tangent squared x equals 1/3, or if we take the square root of both sides, the tangent of x is 1/3 plus or minus the square root of 1/3, or plus or minus the square root of 3 over 3. So tangent's a little bit different. Let's think about what is the trig, or the period for the tangent. The period for the tangent is pi, so we're going to be adding pi in instead of 2 pi in. So we know that in quadrant 1, the tangent is positive. And the angle that has a tangent of a positive square root of 3 over 3 is pi over 6. And if we add pi n, where n is an integer, that would also take care of the third quadrant angle. We also know in quadrant 2 that the tangent is negative, and the angle here would be, the angle here would be 5 pi over 6. And if I add the period, that would put me into quadrant 4, which would catch that fourth quadrant angle. So these represent all the solutions for the tangent that would make that particular equation a true equation. All right, we're going to look at another problem that's similar to the last one, but this time we're looking at sine again, and remember the period of the sine is 2 pi. We are going to isolate our trig function. I'm just going to go ahead and skip a step here. I think you can see that the sine squared of x is 3/4. So the sine of x is plus or minus the square root of 3 over 2. Again, I want all the solutions. We know that the sine plus or minus, this is going to catch all 4 quadrants. So let's just go ahead and do that real quickly. X in quadrant 1, the sine is the square root of 3 over 2 for pi over 3. And we can think about plus 2 pi n. In quadrant 2, we have 2 pi over 3 plus 2 pi n. In quadrant 3, the last one was quadrant 2. Quadrant 3, we have 4 pi over 3 plus 2 pi n. And in quadrant 4, we have x equals 5 pi over 3 plus 2 pi n. And that n should be right there. Okay, so that would represent all the solutions. But if we want a more concise way, if all 4 quadrants are involved, we could take the first 2 quadrants. This is just more concise. Pi over 3 plus pi n. Because if I added pi to pi over 3, that would give me 4 pi over 3. And then we could take the second quadrant angle, 2 pi over 3 plus pi n. Because if I add pi over 3 to 2 pi over 3, I get 5 pi over 3. So this would really be the preferred way. It's a more concise way to write the solution if all 4 quadrants are involved in finding the correct solution to your equation. Okay, this particular equation involves 2 different trig functions. So what we need to do is try to see if there's any way we can separate them. We may have to use factoring, we may have to use identities, but let's start by putting everything on, in this particular problem, just think algebraically, let's put everything on one side of the equal sign. So I'm going to subtract twice the cotangent of x from both sides. Many of these problems we're combining our algebra skills with what we know about the trig function. Now I have 2 separate terms. I have this term and this term. And I can see that they both contain the cotangent of x. So if I factor out the cotangent, I'm left with cosine squared x minus 2, and that equals 0. So in this case, either the cotangent of x equals 0 or the cosine squared x minus 2 equals 0. So we know that the cotangent of x is equal to 0 when x equals, think about the graph or think about your unit circle, when x equals pi over 2 plus pi n. Remember, cotangent has a period of pi. If we solve for cosine, we have cosine squared x equals 2. When I take the square root of both sides, we get plus or minus the square root of 2, which is larger than 1, so we have no solution here. So here our only solution that would make that a true statement is x equals pi over 2 plus pi n. All right, let's look at another problem that's similar to that. I'm going to put everything on one side, see if what I can do with it. Sine squared x minus twice the sine of x equals 0. Two separate terms. So I'm going to factor out what's common to both. The sine of x, and I'm left with sine of x minus 2 equals 0. So either the sine of x equals to 0 or the sine of x minus 2 equals 0. So over here, if I have the sine of x equals 2, we know that that's larger than 1, so there's no solution. And we know that the sine of x is equal to 0 when x equals 0 or x equals pi. And if we just think about this a little bit, a more concise way to write this one, this would not be incorrect, but a more concise way would just be pi times n. X equals pi times n, because if n is 0, we get 0. If n is 1, we get pi. If n is 2, we get 2 pi. So that's just a little bit more concise way to write it. If we just said 2 pi n, then you would be skipping the odd multiples of pi. So either 0 plus 2 pi n or pi plus 2 pi n, but this is preferred way. All right, now this particular equation is in quadratic form, and on this one I want to just look between 0 and 2 pi. So if I'm only looking between 0 and 2 pi, I do not have to worry about adding the 2 pi in. Okay, so let's think about specific solutions for this quadratic trigonometric equation. If it's quadratic, that means we can probably factor it. And this particular equation, we know we're going to have a 2 sine x and a sine x. And we've got to have factors of -1, and I want a negative in the middle, so we'll have a -1 here and a +1 here. And either twice the sine of x plus 1 equals 0, or the sine of x minus 1 equals 0. So here we want to know, where is the sine of x equal to a -1/2, and we know that between 0 and 2 pi, the sine of x is negative in quadrants 3 and quadrants 4. The reference angle is pi over 6, so x would have to be 7 pi over 6 in quadrant 3 and 11 pi over 6 in quadrant 4. So we've got that half done. Now we want to know, where is the sine of x equal to 1? And if we're only looking between 0 and 2 pi, that only occurs when x equals pi over 2. Okay, let's look at another one. We want to, it's in quadratic form. I only want solutions between 0 and 2 pi. So again, we're going to start by factoring. We know we're going to have twice the sine of x and the sine of x. This time my middle term's negative, but my last term's positive, so that makes it easy, minus 1 and minus 1. So twice the sine of x minus 1 is 0, so the sine of x is 1/2. And we know that occurs in quadrant 1 and quadrant 2, so x would have to be either pi over 6 or x would have to be 5 pi over 6. Over here we need to know, when is the sine of x 1 again? And from the last problem, hopefully we remember that is pi over 2. Now, if we wanted all solutions, we just add plus 2 pi n to all of these solutions that we just got. Okay, on this problem, notice I have mixed trig functions, and it's sort of in quadratic form, but I can't really factor it because I'm looking at sine squared and cosine. So we want the squared term to match the linear, so I need to rewrite sine squared in terms of cosine squared. And we know that that is twice 1 minus the cosine squared plus 3 cosine of x minus 3. I have to simplify, and this time I want all solutions. But let's group. Okay, I'm going to add 2 to negative 3, and we get negative 2 cosine squared plus 3 cosine x minus 1. But since that first term is negative, I'm going to go through and change all my terms. So we'll have twice the cosine squared x minus 3 cosine x plus 1, and this we will go ahead and factor. It's going to factor a lot like that last one that we did, except now we're cosine instead of sine. So twice the cosine x and the cosine of x. We know that both terms have to be negative. So if I set each factor equal to 0, twice the cosine x minus 1 equals 0, the cosine x would have to be 1/2. And we know that the cosine is 1/2 in quadrants 1. X equals pi over 3. And in quadrant 4, where x equals 5 pi over 3. But I said I wanted all solutions, so we add 2 pi n. Because the period of the cosine and the sine is 2 pi. Over here, we know that the cosine of x minus 1 has to be 0. So the cosine of x is 1. And we know that that occurs at x equals 0 plus 2 pi n, or x equals 2 pi n, and of course n is an integer. Okay, here again we have mixed trig functions. So I'm going to rewrite everything squared except for the constant, but I'm just going to choose to rewrite the first one. The secant squared we know is 1 plus the tangent squared. Minus twice the tangent squared. Minus 4 equals 0. So we have 3 plus 3 times the tangent squared minus twice the tangent squared minus 4 equals 0. Now this is not really, I don't have to factor this one. I'm going to group terms. We've got The tangent squared x minus 1 equals 0. So we want to know, where does the tangent squared x equal to 1? If we take the square root, we get plus or minus 1. Now remember, if I'm looking for all solutions, the period for the tangent is pi n, so I only have to look in quadrant 1 and quadrant 2. And we know that x, to get the tangent x equal to positive 1, x has to be pi over 4 plus pi n. Or x is, in quadrant 2, 3 pi over 4 plus pi n.